Everybody see my screen?
Yes, it's working.
All right. Okay, so today I will talk about how we use reactive motions with proximity sensors, and especially for collision avoidance. And let's start with the motivation first. So right now, since we're having the workshop here now, as we can see, we have a growing proximity perception community. So there are many different sensing technologies provided in the past, and also new sensing technology are coming from research and industry right now. So what we want to do is further investigation in the application of these proximity sensing sensors. So together with my colleagues, Hannes, Kistner, and Julian, we're looking at integrating these sensors into grippers, as we can see here in the left image, where the sensors are working in conjunction with tactile and force sensing. And also, as I noted earlier, we have an IROS paper right now published where we're doing, well, which is a further investigation on material detection, where we can, where we have very promising results. So if you place the sensors within grippers or on robotic feet, you can actually infer the material information and then change the robot's behavior according to the material information. So today's topic will be more about the robotic manipulators, where we attach the, where we attach proximity sensors onto a collaborative robot, we can see here, and do collision avoidance. And actually, if you bend the fingers backwards, you can use them also for proximity sensing or collision avoidance. So the overview of this talk will be more like, I will talk about the concept of proximity sensors as robotic skin, then discuss why we use reactive motions and what are the advantages compared to planning. And then I will show our proximity sensing system. And the main part of this topic, of this talk will be an overview of collision avoidance strategies with proximity zeroing. So the concept of proximity zeroing, especially for collision avoidance isn't new. So as Edward Chen, I think, started all this stuff, the inside-out view has some very interesting properties, such as we don't have any occlusion. So we are looking from the robot's view to the outside. And in fact, anything that occludes is an obstacle. So all the data that we're getting from the proximity sensors are very rich in data information, but we don't get we don't have a lot of information or data points. So we have a very large compression of information with proximity sensors, and also compared to depth cameras, compared to depth cameras, where depth cameras provide very large point cloud, we have to process all the data first and then get only those points that are interesting. And that's a very large post-processing pipeline, which doesn't allow us for low latency or fast reaction. So with a small amount of data that proximity perception gives us, we can achieve that to have low latency and fast reaction for the robot. And we also have the idea that proximity always precedes touch, so we can react earlier compared to touch and force sensing, where the contact already occurred after collision. So we can anticipate contact and also do some measures, for example, collision avoidance, or even if collision can't be done, collision avoidance can't be done, we can maybe try to attenuate impact. That's what proximity perception allows us. And so why is proximity perception very good suited for reactive motions? So if we have a look at this image, where we have point A and point B, and we have several different paths, and we want to find the best path to point B. So proximity perception looks as something like this, where we only see, where we don't have all the information of our environment. So the best thing suited for reactive motions is actually a local optimization process, where we react according to the sensors or where we react according to the given state, and we don't have that much information for planning. So if we look at the following diagram, what proximity perception actually gives us is low information or perception information. We don't have information of the, or complete information of the surrounding, but the advantage is that reactive motion is very fast. So we don't have that much computation time, and that gives us very quick reaction times. So compared to global planning, where we require a lot of information, we get very good results for the path planning process. If it's global planning, we get the best results actually, but the downside is that we need very large computation time for that. However, there's no advantage or disadvantage for both of these algorithms. Actually, both can be used in conjunction. For example, reactive motion can be used to keep the robot in a safe state, to avoid collision or as first measurement against collision. And while the global planning solves the solution, we can use reactive motion. And when the global planner has the results ready, we can then turn off reactive motion or keep it on, still keep it on, and then follow the path that global optimization gives us. So that's the idea, to have global reactive motions and planning. But of course, for planning, you require other sensing technologies, for example, camera-based perception. So the objectives are, we want to have contact with multiple obstacle avoidance. So not only one obstacle, but multiple obstacles. And the avoidance reaction should be very fast, as fast as possible. And we want to fill the gap between detection and replanning. And we want to be less restrictive to the avoidance motion, while we want to maintain the desired robot task. So that means we want to exploit fully the redundancy that the robot can give us. For example, if the robot has not only 6 joints, but more than 6 joints. So with these properties, our system, or with this requirements, our system looks as follows. We have 3 proximity sensing cuffs that are mounted on the robot. Each cuff has 12 sensing elements on the bottom side, which measures 8, and at the TCP we had 8 sensing elements. And each sensing element uses time of flight range sensing or distance sensing for far field. And for the close field, we are using capacitive sensing, since we can cover large areas very efficiently with that. However, capacitive sensing doesn't have that much range, which is actually not required. If you have too much range with capacitive sensing, we actually get false detection. For example, self-measurements, which is not that easy to solve or to send our data to the PC, we are using CAN bus event triggered. So if a sensor measures something or detects an object, we'll send the data over CAN bus to a gateway, and this gateway will send the data over Ethernet to the control PC. So since we are using off-the-shelf time-of-flight sensors, which are located here in the middle of the sensing element, I will more discuss about the sensing hardware itself. Our system looks as follows. We are using differential-driven electrodes, which means if we are exciting with a positive sine wave, the other electrode is using a negative sine wave. That has the advantage that if, for example, if we have a target here, even if it is grounded or ungrounded, we create a virtual ground in the object, and that gives us better results or better detection safety. And also, since the electrodes are driven differentially in far ranges, the signals will cancel each other out, and that gives us low EMI. And as we can see here, we have two ADCs, which one is measuring the source signal and one is measuring the electrode signal, which is actually what Edward said, a coherent receiver or transmitter, where we can, if the source has some noise in it, we can measure it. And if we measure it coherently, we can get the noise out of the measurement. So let's come to the reactive motions. So most reactive motions that we see with proximity sensing can be described with quadratic optimization. So where we get the proximity information from the sensors, and according to the sensors, we can set constraints to the quadratic optimization and then create from the given Cartesian motion that we want to make, we can then calculate the joint motion that that solves the quadratic optimization. So let's start with the cost function that we want to minimize. This first has nothing to do with the avoidance motion itself. This one is just creating the task motion that we want the robot to move, or the end effector to move along a certain direction in Cartesian space. So we have this here, the commanded Cartesian motion, and here the robot motion. And what we do is we minimize the task error between both. And further, we have here the joint velocities, which we want to minimize, which is just, we don't want high joint velocities, otherwise we go into singular configuration of the robot. So that's the standard approach which we usually see for differential kinematics. So in order to incorporate obstacle avoidance, what we often see are repulsive motion in the opposite direction of the obstacle. So this can be described as an equality constraint. So the given minimization term is constrained with this equality constraint, where the point in contact or anticipated contact is asked or tasked to move in the opposite direction. So this is the opposite direction, and this is the motion that is created by the robot. And this error should be 0. And with that, we can create this repulsive motion in the opposite direction. However, since this motion is very robust against collision, do we see this video? No. It's not really working in this video. However, this motion is very robust against collision. However, the problem is that it gets very easily stuck in local minima. So we have an attraction force to the goal that the TCP wants to go. And if we have an obstacle that is in between the goal and the robot, we have an equilibrium state between attraction and repulsion. So the robot gets stuck in a local minima and it won't move. So to solve this, and actually if you look at the constraint, it's very restrictive. So you asked the robot to move along a given motion, but you still want one part of the robot to move in a certain other direction. So we want to be less restrictive, which can be actually done with a plane. So a plane is less restrictive than a line, which is motion which are sideways motions. And this can be described with the following equality constraint, which is just we don't allow the robot to move in the direction of the robot and leave the options open in the sideways motions or sideways direction. So in the video, as you can see, the robot is able to move around the hand. However, the plane is still more restrictive than a 3D shape. So the next step, which was released at ICAR 2021, we use a sphere. So instead of using an equality constraint, we are using an inequality constraint. and modulate the approach velocity, which was priorly set to 0. Now the approach velocity is modulated according to this graph. So if we are very close to the obstacle, we have certain repulsive motions. We don't allow positive velocity, and if we are far away, we allow certain velocities towards the obstacle. So that gives us, for example, in this situation, the robot can actually move towards the obstacle, but if it gets close to an obstacle, the robot is only allowed to move in this direction. So with that, we can describe all this with standard quadratic optimization formulation. And all the stuff that we've seen earlier react more or less as passive behavior. So if there's if the robot gets stuck between two objects, it may get stuck in a local minima. So what we want to is to move around it. That can be described with the following. We look at the sum of the obstacle distances and try to increase it, basically. So we create a Jacobian of these distances, and then create another inequality constraint, which just says maximize the distances. We can add these then in this general quadratic program notation. Here at first we see the desired motion and the damping, which are just the motion that the robot should go. And we have the passive and active obstacle avoidance as linear or as equality and inequality constraint here, or in this case, inequality constraints. And since all or most robots have joint range limits, we can create this with boundaries of our quadratic program, which just bounds the parameter set, our joint velocities or joint, the parameter set of our quadratic program. So our solutions are bounded within the joint range limits that the robot has, which can be described in the following. So we can use standard solvers with this, such as MATLAB or any other program. Just type it in, we get really quick results from that. And then the results just look as follows. If you see here in the video, it plays, we are moving out from a singular position and let the robot move from point A to point B and then put an obstacle in between. And since the obstacle is at the TCP, the commanded motion can't be fulfilled, so the robot moves around it. And if we can see here, all the proposed motion or the methods that we have seen are able to keep the distances to the object or avoid collision. However, if we look at the distance to target plot, so what we can see here is, for example, point A, then point B, and then again point A. So if the robot reaches the point, the target changes to the prior starting position. So what we can see with a repulsive motion, the robot gets very easily stuck in a local minima and doesn't move anymore. With the tangential or sideways motion, the robot is actually able to move around it and reach its original position again. And with the less restrictive motion for collision avoidance, we can very easily move around it. So that's the results with regards to moving around an object. And of course, we can still keep the joint range limits. So to conclude everything, we have here collision avoidance implemented as constrained quadratic optimization. And this generates instantaneous joint motions based on the current state of the robot and the environment. And reactive motion maintains the path as long as possible for the commanded task and uses fully the redundancy of the robot. If it's not possible, then the TCP will move from its commanded motion away. Since we're dealing with proximity information, we don't need image processing, which is very computational heavy. We only have a few data points. So we're, in this regard, also very fast with processing. And actually, this reaction motion provides a safety mechanism, which should actually be implemented with other existing safety layers, for example, impedance control or other collision avoidance as other safety measurements or measures. So in the future, we want to combine reactive motion with planning. Actually, I just saw at IROS 2021 paper about this, but it was not about proximity serving, but just reactive motion and planning, which was very interesting. And also, proximity perception, of course, is not only limited to collision avoidance, so you can do exploration, path planning, and impact attenuation, which will be this year submitted to ICRA 2021. So if reviewers are present, please be kind. And yeah, so the idea is just if we can't avoid collision, maybe we can use the information to attenuate impact. So that was my talk, and thank you for your attention.
Thank you very much, Itao. Are there any questions from the audience? Christian.
Thank you very much for your interesting talk. I'm curious about the sensor processing. So you're using a combination of capacitive sensors and time-of-flight sensors. So for the time-of-flight sensors, you get range data. And how do you process the capacitive data in your framework?
Right now, it's just a threshold. So if it's below a certain threshold, we use this measurement as, or we think that a point is, or we define a point that is very close to the robot.
Okay, thanks.
Yitao, actually have a question wondering about your collision avoidance experiments. So you mentioned the advantage of proximity perception in terms of processing speeds, right? So low latency. But have you tried did you perform any high-speed experiments where you can see get a hands-on experience on what is possible?
So right now, well, the algorithm works below 1 millisecond. So even with MATLAB implementation, it's very quick. You are doing only one-step optimization, which is very quick. Right now, we are bounded by the robot control, which has 50 milliseconds or 50 hertz of update rate.
Okay, but so yeah. In this case, you wouldn't really want to increase the operation speed of the robot because it's a 50 hertz.
Yes.
Limit you.
Yeah.
Okay. Barnaba?
Your microphone is muted, Barnaba. Yeah, sorry. No, this was very interesting. I also have a question regarding the experiments that you had. So let's say that, for example, you have like you had the box before, right? And imagine there is the box and then there is another box and the robot TCP or the robot has to reach a point which is somewhere in the middle. Is this then covered somehow? And how do you deal then with the priorities? So which obstacle should be sensed first and how can you sense, for example, both of them at one point? Yeah,
interesting question. Usually with repulsive motion, you get something like an equilibrium state. If you have two obstacles and the robot is in between, I think with the standard repulsive motion, you will just stay in the center of both obstacles.
Yeah, but like imagine you have, for example, a tunnel, right? And you have to reach a point which is at the end of this tunnel, and you have the two walls, for example, or the two obstacles. Can you then keep your task, or you will always stay in a position where you constantly oscillate between the two, for example?
Where with repulsive motion, you can see it as similar like a potential field. And the most optimal position would be in the center, actually. And you could actually move into the tunnel, I think that's not proper. With the tangential motion, that will be difficult, I think, since you're asking the robot not to move towards the obstacle and not in the other direction. And it maybe create something like a circular motion within the tunnel. Yeah. And that might be a problem, but maybe we can, maybe there's a solution in combining all these three strategies.
Thank you.
Yeah. Also, I would like to thank you for a very interesting talk. It's actually great how we see that proximity sensors can be used here in the control with a comparatively simple extension of the control algorithm with this constraints that you added here, and we get actually quite nice results that you obtained, and you showed pretty impressive. So, but here at the moment, you basically just consider 1 point per object with the shortest distance. Would you see that if you have like the kind of more points, or even the shape of the object, would you think that this could also be easily integrated or considered in this algorithm?
Right now, it's multi-point. You can actually detect multi-point, and also the algorithm, will optimize for them. So it's a whole arm and multi-point optimization. However, okay, right now with the time of flight sensing, you have the limitation of having only one measurement point, and with that you don't have the shape information or the surface or the plane, which is very interesting for me actually, or could be used. However, with right now, it's very hard to detect a surface or plane. So you only have a point, and you assume that, you can't it's very difficult to move to something create like a sliding motion across the surface, for example, since you don't have the surface. But with new sensing technology, for example, the new iPhone 12, it has multi-point LiDAR within a single chip. Maybe with that you can create or detect surfaces.
So your framework basically would allow it already now, but yes. In this case it's because you just have this single point sensor. Okay, thank you.
All right. Are there any more questions? Otherwise, I would like to thank you again, Yitao, and we can start the presentation of Christian and Barnaba.
Yes, thank you.